We're now ready to prove the Rada-Nikodym theorem for slightly more general, the sigma finite version. So last video we saw the finite version. So for the sigma finite version, so now let's assume mu is a sign measure and mu is another measure, a positive measure, and I have the sign measure is absolutely continuous with respect to mu. And the sigma finite is important here. I need to assume both the mu function and the nu function to be sigma finite. So here, nu being a sign measure, I require is the absolute value of nu, basically the positive plus the negative part. That has to be a sigma finite as well. Well, then basically the Rada-Nikodym theorem for the finite version also translates here. So there actually exists an f, so that the nu of e is going to be the integral of f d mu. That's for every e inside the sigma algebra. And this f is unique mu almost everywhere, okay? And in fact, this f can be chosen to be a difference of two non-negative functions. One of them is L1 function, in fact. But anyways, we don't need that much. All right, so let's prove this theorem. So let's start by considering sigma finite but positive measures. Okay, so let's assume nu and mu, they are just sigma finite but positive. Okay, let's forget about the sign measure later. All right, so because they're sigma finite, just by definition, there exists a sequence of, say, En, where the union of En is going to be the entire set, where mu of each of these En is finite. And you do the same for mu, so there exists a sequence Fn, their union is the x, mu of the Fn is less than infinity, okay? Well, if I have nu is equal to less than infinity, absolute continuity doesn't really say whether mu is less than infinity, so we need these two sequences. But anyways, I can just let their intersection be something like Kn, so Kn is the En intersect Fn. I have the mu of these Kn and the mu of these Kn are going to be less than infinity, and the union of Kn, you can convince yourself that it's just equals to x, okay? So basically, I just showed if I have two sigma finite measure, I can pick some Kn with finite measure, union equals to x, so that each of these Kn, mu and nu, they're both finite, okay? And we can also make sure these Kn are actually disjoint by doing the standard trick, replacing, let's say, K2 be the set difference of K2 and K1, and so on. Okay, so without loss of generality, let's assume these Kn are just disjoint, okay? All right, so on each of these Kn, well, I can actually just restrict our measure. So if I consider nu restrict to Kn, by the way, by our definition is just equals to mu of A intersect Kn. We probably put that on your assignment 1, I think. All right, and you do the other one, you do mu restrict to Kn, as again by definition is mu intersect Kn. They're just finite measures, okay? They are all finite measures, okay? And pretty sure it's one of your assignments. And because they're finite measures, then I can find some Fn, okay, so that the new measure, the nu restrict to Kn of A, is equals to the integral over this A, okay, of some of this Fn, okay, Fn d mu restrict to Kn, okay, and because the Kn complement is a null set with respect to this mu and nu, so I can assume that this Fn is supported on this Kn. Okay, I can assume that Fn is 0 on Kn complement. Okay, by replacing Fn on a null set, it doesn't change anything. Okay, the formula still holds. And basically what I proved is the following. If you just write out the definition of these restricted measures, so on the left-hand side, I have mu of A intersect Kn. That's just equals to the integral of A over this Fn. Well, I can write Fn as just multiply a characteristic function of Kn, so I can make sure everything is inside Kn of this d mu. Okay, they are really the same. And now I can just apply the MCT, okay? So if I consider nu of A, well, by definition, well, these Kn they are destroyed and they union to the entire thing. So this is just the summation of nu of A intersect Kn, okay, and greater than or equal to 1. So this is the summation of these integral of Fn characteristic function on Kn d mu. MCT tells you everything here is positive, so I can interchange the integral and the summation. So I have integral A, the summation of these Fn, okay, characteristic Kn d mu, okay. Well, technically I don't need to add this characteristic function just to make sure these Fn is really 0 outside Kn. All right, so now the summation, this one is going to convert to some function, let's call it f. Okay, so this is the integral of A of f d mu. Okay, so here f is really just equals to Fn of x if x is inside Kn, and if x is not in any of these Kn, I can just let f of x to be 0. Okay, so this f is defined, even though it looks like an infinite sum, it's really easy to define. All right, so I have my function f, and it satisfies the desired property. Okay, so I'm done for the sigma finite but positive measures. The uniqueness of f again is really simple to see. I'm not going to show that. It's just an exercise, basically the same proof. Okay. So now finally, I need to talk about what happens when nu is a signed measure. Okay, when nu is a signed measure. All right, and we have the absolute value of nu is just the positive part plus the negative part, so it's a positive measure, and you can clearly see that the nu plus and nu minus, they are both smaller than the absolute value of nu, okay, because they're two positive measures. All right, so you can see that the nu being absolutely continuous with respect to mu, well, that just means the following. So by definition, it means if mu of A is equal to 0, I will have the nu of A is going to 0, but we saw that from last class. This just means A is a nu null set. Okay, A is nu null set. And being a nu null set, we saw is when we talk about the sign measure, is just basically saying the absolute value of nu when you evaluate this A, that's going to be 0. Okay, that's essentially the same thing. And that's by definition basically tells you the absolute value of nu in this measure as a positive measure, that's going to be less than well, absolutely continuous with respect to mu, okay? And because mu plus and mu minus, they are bounded above by this mu, so immediately you know, well, if you replace this absolute value of nu by something smaller, then you get something that's still absolutely continuous with respect to mu, okay? And in fact, the other way is really the same, okay? Convince yourself the other way. Once you have two things that's absolutely continuous with respect to mu, you take their sum, that's still going to be absolutely continuous, okay? That's really easy proof. Okay, so all of these are equivalent. So because we know nu is absolutely continuous with respect to mu, so I can know that mu plus and mu minus are both absolutely continuous with respect to nu. And the absolute value of nu is sigma finite, so is the mu plus the mu minus, they have to be sigma finite. They're bounded above by the absolute value of nu, so they're also sigma finite. So everything works. We can just say by the Radon-Nikodym theorem, the sigma finite case, or sigma finite positive measure case, we have there exists a f plus and a f minus, so that the nu plus of A is going to be the integral of the f plus d mu, and the nu minus of A is going to be the integral of f minus d mu, okay? And you take their difference, you get the signed measure nu, so nu is just the integral of the f plus minus f minus d mu, okay? So basically I showed the Radon-Nikodym for the signed measure. All right, so here you can pick, of course, you can pick mu f plus and f minus to be non-negative because they are mu plus and mu minus, they are non-negative measures. All right, and because at least one of these mu plus and mu minus has to be finite, in fact. Okay, so at least one of these mu plus and mu minus, in fact, a finite measure. Okay, so when it's a finite measure, so let's say with a lot of generality, let's assume mu plus is finite. Okay, so the integral of this f plus d mu, okay, that's just equals to the mu plus of the entire thing that's finite. This just shows that the f plus is actually a L1 function. Okay, so in general, this difference f plus minus f minus, it doesn't have to be L1 because one of them can have infinite integral, but you can at least assume one of them is in L1. Okay, so that's the last part of this theorem.